Uh, Good afternoon, everyone. My name is Krishna Priya. I'm a PhD student from Center for Computation and Data Science, IIT Kharagpur. I'm working with Professor Rajaram Lakaraju, and I'm just going to talk a little bit briefly about my work on two-dimensional turbulence over random topography. So the topography under the ocean, it has wide range of variability. It ranges from seamounts to canyons to ridges, etc. And in the late 20th century, Manita and Hossein has actually tried to understand the topography below the ocean, and using sonar, they studied and mapped the oceanic topography, and it talks about the variabilities, wide range of variabilities that are present in the ocean. So to give you a brief idea on what led to my study on this topography, turbulence over topography is, mainly topography affects oceanic circulation in two different ways. One is topographic steering, and it enhances and inhibits mixing. So it affects actually when there is a current, and if there is a topography, it cannot go through the topography, so it has to steer. So many oceanic currents like ACC and Gulf Stream, etc., are actually very sensitive to the topography under it. For example, the Southern Ocean, if it was the topography under it was flat, then the ACC would have been 10 to 20 times stronger than it is already observed. And another motivation that led me to this study is that most of the ocean rings that are actually long-lived and ranges from some tens to hundreds of kilometers actually are persistent in the ocean for a long period of time. And the reasons were actually unknown because the topography was not taken into consideration for their studies. And later, Radko studied that the ocean, the topography under these ocean rings actually cause this longevity of the currents that are actually present. So they have done a study on a rough topography, and they call this the sandpaper model, where actually this kind of topography actually slows down the ocean currents and actually increases the longevity of the vortices above it. So, and another motivation that led to this study is the topography in the ocean can actually inhibit and enhance the mixing. So this shows the vertical diffusivities in Brazil Basin in Eastern Atlantic Ocean, and we can see that where there is some there are no more irregularities, where the mixing is kind of less, and if it is more rough, it is kind of enhanced. So another interesting thing about topography is that if at high latitudes where the stratification is very less, this oceanic flow tends to follow the contours of the topography below it. So that is the basics of my study, where I'm looking at barotropic models on and the flow above quasi-geostrophic models. So here, suppose I have an ocean floor or some variable height h of h, and it is at a mean depth of h naught from the surface, and I'm using quasi-geostrophic approximation and using an unforced initial value problem and pseudospectral method in a doubly periodic domain to understand how the flow above a random topography looks like. So this is my equation of motion, vorticity equation, where the potential vorticity is actually relative vorticity plus the topographic potential vorticity, which is actually eta is f naught h by h naught, where f naught is the Coriolis and h is the height of the ocean floor and h naught is the mean depth. And we will evolve this unforced initial value problem in a doubly periodic domain to understand how barotropic flow evolves on a rough topography. So before that, I want to talk to you about a minimum enstrophic principle. So suppose you have a equation. Sorry. So suppose you have a equation, and where d is the dissipation term, and if it is equal to 0, it is all the energy and entropy are conserved quantities. So suppose I am adding some small dissipation to the system, and since the dissipation is added at small scales, the entropy decays very quickly compared to energy. So at some, there will be a state of minimum entropy with energy nearly being the same as we started. So like in two-dimensional turbulence, since the energy is cascading upwards to the larger scales, there the dissipation is has very low influence. So there will be a state of minimum Q with a given value of V. So to get that kind of state, we have minimized this variational problem with where mu is a Lagrangian multiplier, and we will get a state of Q is equal to mu psi, where the potential vorticity is related to our stream function and the proportionality constant is our Lagrangian multiplier. And this kind of equation can also be derived from our governing equation. If we suppose in a steady state, or my dou q by dou t is not there, and if my dissipation term is 0, this Jacobian will be equal to 0. If Jacobian is equal to 0, then I can write q as a function of psi. So this will be the steady state solution for the equation, and it was said that it is stable according to Arnold's paper. And to understand what will be the steady state for our case, I took a topography, a random topography with a spectral stop of k power minus 2, and I evolved from a random initial condition, and the relative vorticity is shown here. So initially the vortices are merging and inverse cascade is happening, and at a later time the correlation between topography and relative vorticity is shown here. It's a normalized zero lag cross correlation, and after some time we can see that the relative vorticity actually matches the contours of the topography, where the negative vorticity is present at the shallower regions and positive vorticity is located in the deep regions. So we can see that clearly there. So what happens if I am increasing the irregularity of the topography? So suppose I have some particular horizontal scale which corresponds to the previous one, and if I am increasing the randomness in the topography, what happens? So here also we can see at small scales the relative vorticity is kind of correlating with the topography, and also the stream function at large scales is in correlation with the topography. So if I am calculating the correlation functions, we can see that it's anti-correlated in relative vorticity and correlated in stream function. And we can see even if I change the randomness of the field, the correlation with the stream function is not that much changing. So if you are looking at the relative vorticity, it can better and talk about what difference a regularity can cause to the evolution of relative vorticity. So to quantitatively study them, we looked at the integral quantities like energy. So initially, suppose energy is decaying like in 2D turbulence. If I am increasing my regularity, the decay is kind of stronger. There is a fast decay in a small scale topography. And if I am looking at the potential vorticity and relative potential entropy and relative entropy, they decay to a minimum entropy and potential entropy state. And we also looked at the mean length scale, which actually characterizes the organization and disorganization of the flow. So initially it starts from very less value, and it increases to a state, and this change in slope will actually tell us at what age the inverse cascade energy stops, and the inverse cascade actually slows down and the topographic influence is there, so that it goes to a constant value. And we have also studied how this potential vorticity and stream function is related, whether it satisfies our minimum entrophic principle. And we can see that there are so many branches in the scatter plots. So there is no linear relationship between our potential vorticity and stream function. And these branches represent these deep and shallow regions, and at some parts, if we are looking at this scatter plot, there is some linear relationship, but mostly it's kind of a non-linear relationship. And this small scale topography presents a large number of such branches because of that there are so many topographic irregularities. So and just to conclude, I have done the, I understood the behavior of barotropic flows in a rotating system and under the influence of variable bottom topography, and the inverse cascade is halted as the flow becomes aligned with the topography. And this cross correlation is also calculated to understand how the relative vorticity and stream function is related to the topography. And we can see that the global energy decays faster for smaller topographies. And also we checked the minimum entropy principle, whether it is valid. And we have seen that it does not hold over the whole domain. Thank you.
Thank you very much, Krishna. Other questions from the students?
Hi, great talk. Really nice slides. They're very easy to read also. Just one question. So you've not been looking at the effect of friction at the bottom boundary layer, right? The topography is just guiding the flow.
No, it's coming. The energy is decaying due to the viscous effects, right?
So you have a different represent. So okay, so you have viscous effects at the bottom boundary. Okay. Do you have any comment on the time scale over which that acts? So like if you remove the viscous effects and you just allowed it to be guided by topography, you know, so
we always add some kind of dissipation term there, viscosity in the equation itself. That on top of that, there is some viscous effects from the topography also. So if it is not there, I think the flow might. No, the topography is there, then of course the viscous effects will be there. No?
Yeah, physically, yes, what I'm asking. So if you think of the effect of topography, in the long run, all the vortices will stop, right? Because that's a perpetual.
It will align with the topography, yes.
No. Even after aligning with the topography, eventually it will stop. It will decay to zero. So you're getting this steady state, quasi-steady state before it decays away. Yes. So there must be a time scale separation between the time scale over which the viscosity is acting, the frictional gradient is acting to die it down, and the time scale over which it just adjusts to follow the topographic contours based on, you know, trying to seek potential energy minima. So do you know how big that difference is? Or when you ran your simulations, did you wait till the end for it to die out?
No, we haven't. Okay. We looked at this quasi-steady state only.
Okay. Yeah, thanks.
Okay, are there more questions?
So the work you talked about reminds me quite a lot of the work that was published, I think, last year by Sigmund and Young. So could you?
It is part of that, actually. You know, we have done this work just before that publication, actually. And this work actually is in the subset of one case she talked about, where the initial energy is actually less than the some characteristic energy that she was talking about. It's one case of that.
Okay, there's another question here.
I have a similar questions as the student. You have your potential vorticity is the relative vorticity plus this topographic vorticity, and the dissipation operator, which is this hyperviscosity, probably acting on both, right, on the sum, which is a bit weird. But you could also do let the operator acting only on the relative vorticity, right? Would that change your results somehow? Can you think about this?
Speculate about it? It's acting on both. In the equation, it is acting on the potential vorticity, right? Which will be a sum of both relative and potential topography.
Yeah, but that's just a parametrization, right, for some frictional effect. So you could let it act only on your relative vorticity.
It might. I'm not sure. It might change. We haven't looked into it.
And I have another short comment. There's this famous or infamous parametrization for this effect, right? The Neptune effect, they called it. Okay. They wanted to put this effect into ocean models 20 years ago. And there's one citation. all the way, right? It's a famous thing.
Okay, there are more questions? Then in that case, let's thank Krishna once again.